my lovely mug again today. Yeah, so I'll try and keep this a little bit lively. Hopefully, we've had a few debates over the last couple of days about how much we love coral and seagrasses and mangroves. I love all those things too. So I was asked to give this talk. It's gonna actually, I'm going to amend my title slightly because although marine carbon dioxide removal, as we heard this morning, there's elements of it that have potential to mitigate against ocean acidification. It's not the main priority for most carbon dioxide removal activities. Obviously, it's to remove carbon from the atmosphere. So I want to actually talk mostly about some of the strategies, what we're thinking they are, what are the possible impacts, maybe what we need to be considering, and the importance of kind of monitoring. So bringing it back to why we're here this week, but also reflecting through that, I will mention how these systems maybe will change pH and acidification as a result of that. So I hope that makes sense. And hopefully there'll be time at the end for some thoughts from the audience. Um, so what's the problem is that we have carbon dioxide going up in the atmosphere. So in all of the 1.5 degree scenarios for the Paris Agreement, these include some element of carbon dioxide removal now. We've gone past the point of not being able to include elements of that. And we'll talk a little bit about the different, what we call conventional CDR methods and novel CDR methods. And this is just a graph to show where we are, current carbon dioxide removal levels in 2020 were about taking up about 2.1 gigatons of CO2 per year. And if we get to 2050 with no new carbon dioxide removals, and I'll come back to what these are in a minute, then we'll kind of be maybe towards 4 gigatons of carbon per year removal. But if we start to include some of these less conventional CDR methods and novel methods, then we can bring that down. And the reason we need to bring that down is really to do with the rate and time scale that we need to get CO2 emissions down in order to reach the 1.5 or stick to the 1.5 Paris Agreement goal. And this is all to do with rates. So if the longer we keep emitting CO2, the longer we have to keep, the more CDR methods that we're going to have to employ to bring that CO2 back down if that's what we want to do. So we can remove emissions, but to get to net zero in 2050, actually we still need to get net negative. So we need to be removing that carbon dioxide from the atmosphere as opposed to just stop emitting as well. So the conventional methods, this is again from the State of Carbon Dioxide Removal report. But these novel and conventional methods for CDR kind of exampled here. So the top four that you can see that are highlighted with the gray, these are what we consider conventional carbon dioxide methods. So carbon dioxide removal methods, CDR methods. So there's things like afforestation, reforestation, agro-management, forestry management, peatland, coastal wetland restoration, soil carbon restoration, croplands, grasslands. So it's all the kind of planting more trees, keeping the trees either wherever those trees are, keeping the soils in a carbon sink kind of state. All of the novel products, novel CDR that we're talking about, are these kind of more geoengineering type, manipulating the system beyond what we're already have contributed to. So you can see that these conventional CDR methods, they're in a high state of readiness, but they actually maybe don't store carbon for anything more than maybe decades to centuries. And they have reasonable to sort of large to moderate scale mitigation potential. So they're things we should definitely be doing. And I think we are probably in all agreement that restoring the habitats and forests and mangroves and seagrasses is a good thing to be doing. But these novel systems, these novel CDR mechanisms, you can see are mostly either very low state of readiness or maybe a medium state of readiness. And there's so much we still don't understand about these. And I'll then talk about the marine side of things. So when we're talking about marine CDR, we're talking about the coastal wetland restoration for the conventional CDR methods, but things like ocean fertilization, alkalinity enhancement, biomass sinking, and ocean carbon storage. And I'll go through these methods in a little bit more detail. So why the ocean? Why are we interested? As we all know, I'm pretty sure now, the carbon in the ocean there's a much bigger pool of carbon. The ocean is the way it's one of our largest sinks on our planet. It takes up 25% of the carbon dioxide that we've emitted naturally anyway. It's about 50 times a bigger sink of carbon, bigger store of carbon than the atmosphere. And you can see that just in this cycle. And obviously, we'd heard from Patrick yesterday about how the carbonate system is in the ocean. And that's one of the reasons the ocean is able to store lots of carbon, because it's not just CO2, it actually gets transferred into bicarbonate and carbonate ions. But we also have cycling through to production of organic matter that can sink down into the deep ocean and sequester carbon away. So there's lots of potential for the ocean to actually help us to store carbon as way if it's done in the right way. So let's look at these in a bit more detail. So this is taken from the Ocean Conservancy's report on marine carbon dioxide removal techniques. So when we're thinking about conventional biological enhancement, what we're really talking about is this element at the top, the blue carbon enhancement. So it's just enhancing the natural ability of mangroves, seagrasses, things like that to actually take up carbon and store carbon, as we heard nicely from Dr. Auer this morning about seagrasses and their storage potential. These methods here in the middle, so marine biomass, fertilization, dumping, and artificial upwelling, are novel techniques that would enhance the biological pump in the ocean. So they're all mechanisms that would actually speed up the process of biological organic matter production and thinking about locking that away to the deep sea. Alkalinization or ocean alkalinity enhancement is about a novel way of enhancing the carbonate pump. So it's over geological timescales. We get rock weathering, and that naturally buffers the ocean. That's what adds the carbonate and bicarbonate into the ocean. So we're speeding up that geological process. And then the other one that I'm going to mention today, I'm not going to talk about the biomass, the biochar or biomass, is direct CO2 removal from seawater. And that's basically a way of enhancing the solubility pump. And again, we'll come back to the detail of these in a minute. So let's go through some of these in a bit more detail. So coastal blue carbon. So these pictures I really like. They're from the strategy for NOAA's carbon dioxide removal research. So you can kind of look that's online. You can see what NOAA wants to do in the US with all of their research. But actually, the figures from that document are quite nice at explaining the system and what's going on. So as you all know, and we heard nicely this morning, of seagrasses and mangroves, salt marshes, things like that, they're photosynthesizing. If they're net photosynthetic, then they're taking up carbon dioxide from the atmosphere. As we also heard this morning, any respiration of those processes will release that CO2 back into the atmosphere. But then you also have these other gases potentially adding to the complication of the system. So coming back to our debate, we can talk more about that later, whether we need to consider these systems as a whole, or whether we just think about them as carbon dioxide sinks, or whether we think of them as carbon sinks more broadly. So the question remains really, what happens to that carbon once it's knocked away? We heard this morning really nicely that we know that carbon is stored in those systems, but there's still debate, I think, as to how much is stored and for how long it's stored. And as you heard again this morning really nicely, that if you have a warming event or something happens to that system, it gets degraded, then very quickly you get that release of carbon dioxide back into the system. So it's actually not a really good way of locking that carbon away, kind of into the old carbon, if you like, so it doesn't stay out of the system for very long. And then also you have to consider the flow of that carbon off the system as well. So is it going off the shelves? Where is it going? Is the kelp forests or mangroves that are actually like that, those leaves that are falling from the trees, are they degrading? Are they going out to sea, being exported? So the benefits of enhanced biodiversity, coastal protection, ecosystem restoration, all these other things that we know from corals, from seagrasses, from mangrove forests, I think, and this is my opinion of it, I think they likely outweigh the benefits of any carbon removal potential. And I think we really need to be quite cautious about how much emphasis we put on coastal blue carbon as a blue carbon credit, because actually these have so much value in other respects that we need to make sure that they're valued in all of that ecosystem, as well as just the carbon side of it. In terms of whether or not they will help with acidification, I'm not going to spend too long on that because we had nicely this morning about some of the uncertainties associated with that. And I think what we recognize is that variability is going to be important here. So if you have a biological system that wasn't there before, then you're going to enhance the variability on a daily cycle. So whether that's a net positive for the acidification community, look for the response, or whether it just means that organisms are then exposed to more variability in pH because in a daily tidal cycle or daily cycle, they're actually seeing increases in pH through photosynthesis, and then respiration is bringing that pH back down. So they could be just that organisms are then exposed to more extremes of pH as well. So we need to consider that variability as well. And then, as I say, there's unknown impacts for what happens to that exported carbon to the deep sea, possible contributions to deoxygenation and acidification at depth. And you'll hear that come up a lot in this, because I think that's one of the biggest unknowns. We kind of assume that the ocean is big enough to just dump all our stuff in and it'll be fine. But actually, there's huge implications for the deep sea as to what goes on from our coastal systems and from what we do from the surface. So macroalgal cultivation is the next one that we'll talk about. So this is basically where you're taking macroalgae, you're cultivating it in seaweed farms, things like that, in the coastal zone. And then what you do with that biomass is then where the carbon is stored. So you can either store it at the seafloor in coastal systems. Again, it's the same idea. You've got photosynthesis happening. It's taking up CO2. You could take that biomass and actually use it, process it for fuel, for food, for fertilizers, in the place of the fossil fuel equivalents. And I think that's maybe something that has real potential benefit. Or there's people talking about intentionally taking it offshore and sinking it into the deep sea. So I think you're going to know what's going to come up with the impacts of this one. So again, we have the same sort of issues as the coastal blue carbon. So the benefits that will probably be gained from seaweed cultivation and seaweed harvesting for things like fuel, food, bioproducts that you can create from it are probably going to outweigh the potential benefits as a blue carbon store. But I would say that we really still don't know the benefits of that yet. The same thing is going to be true for acidification. There's going to probably be some local effects, but actually we're talking about something that maybe if you stick a load of algae that in a system that wasn't there before, then you're probably just going to enhance that variability again. And like I said before, you've got these unknown export impacts. What's going to happen to that carbon? How long is it going to stay in the system? Is it going to just get remineralized as it goes through into the deep ocean and actually just create more CO2, cause deoxygenation elements? Ocean fertilization, it's the same process again. It's another way, instead of fertilizing or enhancing the macroalgae or the seagrasses, all we're doing here is adding nutrients to a system that would maybe not have either as much macronutrients or some of the micronutrients, so things like iron, enhancing that biological production, and then allowing the organic matter to sink down and be stored in the deep ocean. I think you're going to see all what's going to come up again, very similar. So there was actually a lot of studies done on iron fertilization back in the late 90s, early 2000s, when acidification was kind of first being touted around as well. And there's a lot of studies that did this experiment and where they went out and put iron in places where iron was limited to see if they could stimulate phytoplankton blooms. Many of them were successful in stimulating the blooms, but what actually they showed was that it was a change in phytoplankton community dynamics. So instead of having nice big diatoms blooming and sequestering that carbon and then locking it away through the biological productivity, they stimulated much smaller phytoplankton species that were able to respond much more rapidly to that nutrient addition. And so that nutrient, the organic matter actually got remineralized much more rapidly. And so they actually saw that the carbon dioxide was just being emitted back out again or moved on. So there was very little carbon sequestration happening because of those experiments. So there's no evidence or very little evidence to date that actually this works to sequester carbon. So what we do see so far, and there are people repeating experiments at the moment, is a change in the plankton community and water column carbon cycling. That means that actually the carbon isn't moving out of the water column, it's staying in the surface zones or rapidly kind of remineralizing as it falls through the water column. In terms of acidification, again, you're kind of enhancing biological production, so locally you can elevate the pH, but actually it really depends on what's going on with the carbon system. If you start remineralizing it, then that elevated pH could be short-lived. It's probably going to be quite localized. Again, you have this issue of what's going down into the deep sea. Where is that carbon going? How long will it be stored for? But also, in this case, you actually have impacts on nutrient cycles. So where are you getting your nutrients from? What are you doing to the nutrients on the surface? How is that changing the ecosystem and how that food web will shift? What does that shift in communities with the phytoplankton mean for the zooplankton and fish communities? Will it stimulate harmful algal blooms, things like this, especially when you're thinking about in coordination with warming events, things like that. Artificial upwelling, downwelling is basically the same thing. You're stimulating the primary production through the through the phytoplankton, but you can either do that through transporting deep water into the surface water, so the deep water is rich in nutrients. It has higher CO2 levels, low in oxygen, but it goes up into the surface. You stimulate your bloom, and you allow that organic matter to sink down and get buried in the deep ocean. Artificial downwelling would be the same. You take the surface water so you're enhancing the organic matter, the biological pump down into the ocean. So you take that surface water and put it down into the deep ocean. Neither of these two have been well, I think these are kind of the least state of readiness of all of these ideas. And the magnitude that you would need to kind of be thinking about these things it just seems a little bit off the charts as to how you would actually make these things work. So there's very little evidence that it would work in practice. Sequestration potential is also unknown. Again, we kind of have the same issues from fertilization experiments. Most likely, like the fertilization experiments, you're going to see a change in the plankton communities and water column and nutrient cycling. In terms of acidification, we have the same thing going on, short-lived impacts potentially. But also, in addition to the impacts, is this idea of nutrient robbing. So as you'll know and familiar with, the way the ocean cycles carbon and nutrients around the planet is that actually the surface waters that are rich in nutrient, surface waters get subjected down in the polar regions. That nutrient-rich water gets transported to the tropics where it comes up and is upwelled. And our coral reef systems that rely on that upwelling nutrient-rich water, if we start upwelling nutrients at some other location in the ocean at the scale that we would need to do that to make this work, are we then robbing those nutrients from these ecosystems further down the ocean and moving that nutrient system around? So that's something that I think we have to be really careful about, is understanding the dynamics in terms of the wider ocean, depending on where these things are played out. So the next three are the more geochemical carbon dioxide removal techniques. And these are the ones we've kind of focused a little bit more at PML. We're involved in a couple of projects, really as scientific independent advisors to industrial partners or to policy, to kind of give an independent assessment of either the impact side of things or how you would go about monitoring the effectiveness, the efficacy of these things. So I'd say these are the ones that personally I've been more involved with. So ocean alkalinity enhancement, as I say, it works by enhancing geological weathering processes. So it's sometimes called enhanced weathering. What we're doing here is taking crushed minerals, so things like your calcium carbonates, your silicate oxides. So olivine is quite often considered, limestone, things like that. Those minerals are extracted, mined, crushed, and then dispersed in the ocean. And there's many different ways that are being proposed. So many different minerals are being proposed, different dispersal mechanisms are being proposed. And so there's lots of nuances about how we do that and the impact that that will have. So some people are looking at just putting olivine rocks onto shorelines as kind of extra shoreline protection, but maybe they also have this CO2 potential, CDR potential as well. Some people are talking about dispersing very fine scale minerals in the surface oceans, and it needs to stay in the surface oceans to work, to be able to absorb the extra carbon dioxide. Some people are talking about making it into solutes and then dispersing that solute into the ocean so that actually it has a bigger carbon potential. And if you think of ocean alkalinity, if you think of the ocean as a carbon sponge, ocean alkalinity works by actually just expanding that sponge. So the CO2 will go into the ocean, into that sponge, and if we make the sponge bigger, we can just take in more carbon dioxide. So if you think of ocean alkalinity in that way, it's just like making the potential to take up carbon into the ocean a bigger potential. The other way that we can do ocean alkalinity enhancement is through electrochemical approaches. So what they were proposing in this way is that you would take in seawater into a plant, you would acidify, you would manipulate the seawater to create an acid and a base, so hydrogen ions and your hydroxide ions. And then there's different things you could do with that acid. You could either neutralize it and pump it back into the sea. You could transport the acid and use it for market processes. Or there's some people suggesting that we just dump it in the deep sea. Enough said on that. And then what you would do is you'd take the hydroxide out to sea and you'd use that as your alkalinity, adding hydroxide so that actually it can take up more carbon dioxide and it would also change the pH. So neither of these two different ways so the electrochemical approach is being assessed as we speak. Many industry people are looking into it, as well as the mineral release approach. So there is potential carbon storage from these methods, from the modeling studies that have been done. And there is also potential local amelioration of acidification, because what you're doing is you're adding that alkalinity, so you're allowing that to absorb hydrogen ions. Having said that, actually, that's a sort of unequilibrated state. So if you think of like, you've got your state as it is now, you add a load of alkalinity, and then actually what you want to do is to absorb all that carbon from the atmosphere into the ocean. So by absorbing the carbon dioxide into the ocean, you change the DIC. So on a short-term scale, yes, you locally ameliorate pH, but actually you're kind of then changing DIC as well. And if you remember from Patrick yesterday, if you change alkalinity and DIC, then you actually can either stay at the same pH, or you actually change the amount of pH that you see. So it's not quite as simple as saying let's just add a load of alkalinity and it'll stop ocean acidification from happening. You really need to understand how much carbon dioxide is then going to go into that system, what it's going to do in terms of, is it going to become bicarbonate, CO2, carbonate, where is it going to end up at the end of the day? In terms of impacts, what most people are thinking about with ocean alkalinity is the pH impact. And so if the pH impact is minimal, then the potential impact to organisms is minimal, but I'll come back to this further on. But again, it really depends. So people are modeling ocean alkalinity and saying that we can actually add, on a global scale, relatively small changes in pH worth of alkalinity, but so potentially there could be minimal impacts to organisms. But I would argue that there's real unknown potential impact for many sensitive species, including the calcifiers, shifts in ecosystem dynamics, which we just don't appreciate yet, with all of the nuances that go with these techniques. So the other things that need to be considered are things like, especially with the enhanced weathering technique, is that actually if you're adding minerals into the system, you could be enhancing the turbidity, you could be silting the benthos, so putting those particles, where are those particles going? Are they staying in the surface water, and is that impacting the light? Or are they going down to the benthos and they covering up your corals? And then also a lot of the minerals that come up are actually associated with a lot of toxic metal compounds. So how are those toxins going to be released? How are they going to impact the organisms that are in that seawater? And then finally, direct ocean removal. So this is where basically we're taking in, again, in a plant form, so in an industrial process, you take in the seawater. As we had yesterday, the carbonate system, so you've got CO2, bicarbonate, and carbonate ions in seawater, the majority of which the carbon is in bicarbonate form. But that's a pH-dependent scale. So what we can do, like we do for DIC, if we're actually measuring DIC, you acidify all of the seawater, all the carbon gets transformed into CO2, and then you extract that CO2. So what this method proposes is that you take in some CO2, take in some seawater, you pump it into your station, your industrial process, you acidify that seawater, you extract the CO2, and then you can do whatever you want with that CO2. So much like carbon capture storage potential that already operates on fossil fuel, on kind of some of the um, like industrial processes that we have, you then either transfer your CO2 to use or to bury in carbon sequestration, so CCS kind of approach. And then you add back into the seawater that low CO2 water that you've just created. And as you add that CO2 back into as you add that seawater back into the system, um, it actually has a greater potential to take up more carbon dioxide again. So whereas alkalinity was an enhancement of that sponge, making that sponge bigger, if you think of direct ocean removal as what you've done is you've got your sponge, you've squeezed it, you've taken out the CO2, and then you release the sponge again and allow it to fill up again. So it's actually much easier to say how much carbon you've stored because you're actually extracting it out of the seawater and you can quantify how much CO2 you actually end up with in your container at the end of the day. But there's also issues with the fact that you're actually depleting this discharge water of kind of 98% of its carbon. So what is that carbon going to do? What's that seawater going to look like for the organisms that live in it? So there's very little or no direct impact on acidification because it's not changing the system in terms of carbonate chemistry. And I won't go into that now, but happy to talk about it if anyone wants to. And again, you have the same issue that if pH or the carbonate system is minimally changed, then the impact to organisms should be minimally changed. But actually, at the point of discharge, you have very much created a very different system, and you've got low CO2 in that system. So anything that relies on carbon, so photosynthetic organisms, we're talking about seaweeds this morning and sea grasses this morning, and how they actually enhance production in high CO2. Obviously, in low CO2, photosynthetic organisms struggle, and calcifying organisms have potential to be impacted. So there's other sensitive species and shifts in the ecosystem. So we're working a lot on this to try and understand some of those other impacts, and what they could be and what they look like. The premise is that this would be very localized effects, so it would be quite rapidly diluted back to normal sort of seawater conditions. But again, when you start to think of the scale of these things that we would need to actually achieve any global carbon dioxide removal potential, I think you really have to start to kind of wonder about how much impact that local effect is going to be. And also where these things are going to happen. So if we're talking about having these things near coasts, and they need to be in the surface water to allow them to have CO2 absorbed, then are you going to have it near a seagrass bed? In which case, you're going to kill off your seagrass. Are you going to have it near your mangrove forest? So you're going to actually completely destroy that forest system because you've actually just released a load of low CO2 water into the environment. So there really needs to be a really good understanding of the system, how it works, but also then thinking about the locality and the place that you actually put these things if people decide to go ahead and do them.
With these ideas, it sounds like an impact made by hospital. Yeah. I scientific my name and stuff like that. Do you know who that where it come from?
This idea. All of these. I don't know where they start from, but it's people thinking they can manipulate a system, I guess, like. Yeah. But this is.
One look, and you could see space. National Geographic went out with us, and but it didn't. They, I don't think they ended up publishing a detail, but
Yeah.
they've done it. I'm not saying it's the right thing to do.
No,
I'm a
people
teacher,
try them.
so I just
Yeah, yeah.
just use the crews
Yeah.
that they could do it.
Because I always tell my students, right, before you do the experiment, think of if it works out, what you're gonna get at the end.
Yeah.
This sounds like, you know, the end.
And this is exactly the problem. And it's kind of PML stunts is that people are doing this and people are coming up with these ideas, and you're going to get industry that they have no clue on either the carbonate chemistry or how ocean dynamics work or how the biology works, right? So
Yeah.
they need to have scientists work and say, this is the evidence for whether it works or not. And then we can make an informed decision.
The only problem is countries are going to be offered ways to beat their climate crisis and make money by companies selling them these items.
We're paying parents Canada to dump iron on Cuba. Like,
Yeah.
Yeah, but this has been a great opportunity to do, and actually sometimes to do lots of things.
like, yeah. Like,
Yeah.
We were saying earlier as well, there's also government interest because, of course, the whole thing about mitigating and reducing emissions, but actually, government, finally scientists have said, yeah, we've got this on idea. So I think there's quite a lot of dangerous
Yeah.
ways that this could take function.
Yeah.
The scientific.
Thinking that the risk is higher in developing countries because often they're the areas with the least amount of scientific understanding of how the systems are working at the moment. You know, we see with large observations,
countries that are buying into carbon offsets, where we're paying for them to dump things like concrete structures on reefs in Southeast Asia or buying carbon credits here. We don't necessarily the people in the developing world and carbon credits.
I know.
They're feeding their kids.
you know, they're paying,
Yeah.
paying the countries to license them and do it. We have
What's it's plastic in Malaysia.
Oh.
Climate chemistry system around saying is really poorly understood. Far less understood than between Australia and the chemistry system of the Northeast Atlantic Shelf. We are in much better positions when we have. That's really bad thing to do. So in areas where the electricity and our system works, the risk is that much higher of doing something within Canada in main harm with the
Focus on developing countries to regulate that. So in Canada, regulating it so it doesn't dance. That instead of probably like the developed one, when it's like the developing one, when the developed one is problem from running down the speed, maybe have options this like this to the main as and the same is not for the future. It's trying to be practicing but losing something like practicing millions of millions that are trying to that is a long
we're very talking about the ability to manage it. We had a conversation about change international law. That's a different one. We have to make sure our science is responsible for the environment. Scientists understanding these systems they happen to be working, and because they really can. Arguments for suggestions. We should come and do this here because this is a good thing to do. So
I completely agree when we have to on some of these
Okay. Yeah, I understand that too.
I'm just trying to see if I can have the last thing. We need to get it. We need to have some of this.
Okay, go.
Right?
So I'm gonna wrap up relatively quickly, but like so some of the things, the other things to consider. So we've a lot of people are only considering pH when they think about some of these impacts. All to say is that actually what we did was a kind of look review for some of the this was particularly for the direct ocean capture work. We have a PhD student looking into this. And just with a quick mapping exercise from what we know from acidification experiments, from what we know from just general physiology and the interactions with processes, is that if you think about all of the physiological processes that interact with some CO2, pH, and alkalinity, and actually when CO2, pH, and alkalinity, and actually when you start to think of beyond the organism level, you can start to see where maybe, so this is just alkalinity enhancement, direct ocean removal, but you've got the ecosystem where they're going to be impacted. If you dump a load of alkalinity, how's it going to impact the sediments? How's it going to impact if you put new olivine structures? Is it going to impact your wave structure? And then obviously you can translate that up to ecosystem services level. So if you change secondary production because you've added a load of alkalinity to the system, then you've got consequences for your ecosystem services. So we tried to kind of do a mapping exercise for that. So I think there's just to highlight, not to go into detail, but just to highlight there's many other things that we need to consider rather than just CO2, pH, and alkalinity. And again, I don't want to kind of read through all of this, but there's other unknowns. We really just emphasize the cautious approach that we need to be taking. Everything from biodiversity shifts, species displacement, impacts on the carbon sequestration potential. If we alter the system, are we going to alter how that long-term carbon cycling happens? We could introduce new species. We can disrupt sensitive ecosystems. We can change the way that a system is resilient. So systems can be very resilient, but actually, are they resilient if you rapidly alter it? And we know that from our big experiment that we're conducting at the moment by adding a load of CO2 into the atmosphere, that actually doing things much more rapidly than the natural system works is not a good thing. So do we really want to be playing with that again? Just to kind of come back to Jean-Pierre Gattuso and others' work from 2018, this is quite a nice paper that looks at all sort of CDR potential or different options for ocean solutions. So even things like removing pollution, dealing with overexploitation, and whether they actually have a potential to moderate against things like warming, acidification, and sea level rise. So they put things like adding alkalinity as a high potential to ameliorate or moderate acidification. But actually, these numbers reflect how well we know it. So 3 is kind of maybe know a bit about it, but not everything about it. Whereas something like cloud seeding or ion fertilization, some of these other type of really grand scheme geoengineering potentials have no effect on acidification. So we can keep on emitting CO2 into the atmosphere, but actually we're still going to acidify the ocean as well. So we might affect the warming, but you don't affect something like acidification. So the best things to do actually are kind of switch to renewables, deal with pollution, protection, restoration, all these things that we know are good for the system, bringing it back to alignment with how it really should be functioning. So yeah, coming back to monitoring, why do we need to be monitoring? Well, as we've heard, we really want to have that baseline understanding of the system. So carbonate chemistry, we want to understand what the carbon dynamics are doing so that we're in a better position to exactly say whether or not it's going to make any difference, how it will be cycled, what will happen to that system if you mess with it. It also allows us to look to see if carbon is being sequestered. So what's the efficacy? How do we monitor, verify, and report on that technique? It can be used to look for disruptions against the normal carbon dynamics. The same for baseline biological and ecological monitoring. We need that data to be able to understand what the system is doing, where that carbon is going in that system, but then also like the disruption to that system or detecting recovery of the system. We need to be feeding that data into models to be able to accurately say whether or not these practices are going to be scalable, where they need to happen if they happen, and how we can monitor and verify them. We need to be providing support for regulators and industries to actually provide better environmental impact assessments prior to any field trials. Do we have enough understanding of the impacts in the lab, or where these things are going to go, or what the data, what the carbonate system is doing, to be able to provide a decent environmental impact assessment for the regulators to say yes or no, they want this to happen in their waters. And again, all this monitoring and data can support decisions for regulating and planning. Where are we going to do it? Are we going to do it? Do we need to just do it in winter where maybe the carbon is low? Do we do it in summer? But I would argue there's lots and lots of queries as to thinking about regulation is a whole different ballgame. There's a lot of ethics and moral discussion going on in the CDR world. Where do we do it? And then also, like, if you have 5 companies that go and dump alkalinity in the middle of the ocean, how can they claim whose carbon is whose if they sequester it? There's whole sorts of like legal issues associated with this. But I think the important thing is that the data that you are all gathering really needs to be aware that data is really important as we move into this space, and it is a moving space. There are genuinely people coming and asking and knocking on doors, and there was, I think it was Canada, there was recent river liming going on, and they're claiming that we did it for acid rain, so it'll be fine for this. So it is happening, and I think the key thing is to just have that data and knowledge available to make sure that we give a good scientific informed decision. So I will conclude there. So conventional kind of blue carbon, I think has so many co-benefits that we need to stop thinking of it just as blue carbon. Novel CDR is still really unproven in terms of their long-term storage, in terms of their cost effectiveness, and in terms of their impact. We really need to be transparent moving forward. We need to be working with industry to make sure that they don't just go ahead and do these things without that scientific understanding. There needs to be clear guidelines on how we monitor, report, and verify. We need frameworks for the environmental side of that, as well as just the carbon side. And really just to emphasize that CDR is only effective if we actually reduce emissions. If we, as Steve likes to say, it's like thinking of a bathtub with the taps turned on. If you don't turn those taps off, the bathtub is still going to overflow. I mean, you can get a spoon or a little tin and start bailing out the water, but you're still going to overflow the system. So we really, really need to emphasize that this is not taking away from the fact that we need to reduce emissions. So I will end there and welcome the discussion. Do you want to?
I have a question about the environmental impact assessment for, I suppose, even large scale mesocosm type experiments. Is this something that's normal, like in the UK, Australia, US, that researchers have to do like an impact assessment before they run these experiments? Or is that kind of like a maybe not kind of scenario?
For the large scale, like free open ocean mesocosm experiments, probably not. Yeah, I would say no for most of those. I think where we start to have to go through environmental regulations is if we were running a field trial. So if we wanted to manipulate the system outside of a mesocosm, like actually like in the field, then we'd need to apply for regulation, go through regulations. Yeah.
Yeah. I think there were a few there were a few iron fertilization programs that had been done off Sulu Seas, so between Philippines and Sabah, Malaysia, and also it was not recorded or published what the impacts were of that, and neither were actually any kind of form of risk management was done. So actually, nobody knows what were the impacts of that, and that's a bit of a worry because, as you both have rightly said, both have pros and cons, and I think in a way the risk is on the developing countries because in our state as well, we have a really long coastline with a lot of seas that some are in contention. But we have also the government have committed to doing like the carbon capture storage. And a lot of those that you have mentioned is actually what the government says they have committed to do. But yet, there's no pathway for us to input into that. So we don't know what's the risk. And yet, the government's already committed to it. And I can see, like you say, those facilities need to be built. Energy is needed. So I can only see it as only engineering options. Why only the engineering options as well? So I we still struggling with that, and neither is the marine conservation um, scientists large enough to handle this by themselves. So it needs to be a larger regional approach, I think, as well to look at how's this going to affect Sarawak, but how's that going to affect our neighbors? And it's going to be a transboundary issue in the future, but we just don't foresee that yet. Just a short comment on that. But maybe in Europe, where you have a lot more transboundary seas, maybe you have some experience on how that's going to be achieved regionally.
Yeah, so at the moment there in Europe there isn't anything where we're actually conducting any of that activity, but the regulations are probably still quite high. So where it's in EEZs, it's up to the nation to to regulate it, and the European regulations are all to do with good environmental status. So they have to prove that they're not going to affect that good environmental status. So I think we're okay for a while on most of these things, some of them. Um, but there's going to be debate, I think, at the next UNCLOS meeting, so the London Convention, about how actually we regulate these things in the high seas and the open seas. So that's when we get to go beyond jurisdiction. There's still, at the moment, they certainly alkalinity enhancement is considered as dumping and it's not allowed under the London Convention. But whether they'll start to change that with pressure from.
Well, there's also sorry, that there's also a little bit of confusion on the international law side as well, because my understanding is the CBD 2010 said halt to geoengineering. They're really against the whole thing. They think it's misplaced effort, it's unproven, let's not waste our time on it. Whereas the UNFCCC is a lot more open to we've got a climate crisis, we need to do something. So I was at the CBD meeting in Nairobi, and the group there drafted a letter to write to the UNFCCC to say we've already decided at the international level that we shouldn't really be going down this path, but that's not been picked up by the UNFCCC yet. So there's a lot of debate in international law at the moment as well to how much this is, you know, being pushed. So yeah, you've got the transboundary issues and the things you're talking about practically, but at the global political level, there's also quite a lot of confusion at the moment, which needs to be sorted out.
Thank you. Um, I just would like to add a real experience as part of because I'm working for a national agency, a research agency, government agency in Indonesia, and I know there are some initiatives from the US, like startup or private companies, initiative to test or to do some pilot testing initiative in carbon dioxide removal. And what I would say this is really large experiment is that one of the plan is to deploy 12,000 tons, metric tons of unit some kind of olivine stones. 12,000 metric tons of stones in the specific oceans, but it's not, the plant is not in in open oceans. It's just a kind of closed oceans, so that they can control the and monitor the carbon sequestration's capacity. And they predict that if everything is as planned, goes as planned, then it could remove kind of 9,000 tons of carbon dioxide. Now, so when I was approached with this kind of ideas, I was thinking like, whoa, I- because honestly, I don't know the current, regulations at the global level, and at national level as well, and the regional level. I don't know this is how this sits in this situation. Whether this is, would it be illegal, or would it be? That's why in this kind of discussion, I think it really needs some kind of a push in terms of a standard framework, maybe at the UN level, or treaties or something like that, about this kind of technologies. Because 30,000, 12,000 tons, I would say this with this scale, there must be impact.
Was saved it completely.
That's right. That's right. That's right. Thank you.
Yeah, it's a really good example, but yeah.
I'm like I'm your 2 points on the co-benefits for conventional MCDR and a novel MCDR. I'm just like wondering what your opinion is, whether or not we should be investing more in trying to better conventional MCDR, in this case maybe like blue carbon, and or should there be like more of where would you think the investment should be? Because MCDR with the conventional, say, blue seagrass restoration, there's also a lot of technology, a lot of things that we don't know how to do it. What's the survival rate for seagrass transplantation still is extremely low, right? Yeah, I mean, I'm just curious your take on things.
Yeah, I mean, blue carbon's not an area of expertise that I have a lot of. There's other people probably better placed. Personally, I think a lot of this is misguided. It's kind of an excuse for not just getting on with the job of reducing emissions, right? To some extent. I mean, yes, we should be restoring our habitats. Yes, we should be making them back to how they used to be, and I think it would be a better world for everyone if we had more forests and more trees and mangroves and seagrasses. But there's so many, like you say, so many unknowns still as to where we need to put them, how we plant them successfully, the amount of effort that goes into doing that. Um, so the cost effectiveness of it is, yeah, compared to the just getting on with the job of reducing CO2 emissions. It distracts from it all. So we need to be doing restoration, and we need to be bringing back our habitats for arguably probably for biodiversity reasons rather than carbon reasons. I mean, the carbon benefit is a kind of bonus of being able to do that, but I really think we need to just have more action on CO2 emission reduction, personally. But
Hi, I'm Boo from University Malaysia Terengganu. It's a bit fun. So question is, has anyone ever run a life cycle assessment on the carbon footprint of all the methods? So once you want to build all the facilities, you need energy to build those facilities. And then after that, you dump it into you just sequester the carbon into the seafloor. So after the plus minus all the calculation, is it marginal, or will it help? And how long does a facility last? right? If you can build that facilities and it can only last for another 5 or 10 years and it only marginally increase the sequestration rate, is it worth it, right?
And that's an excellent question, excellent point. So life cycle analysis is done. I think when when each of the industries and startups kind of say they're going to try these things, then they have to take into account the life cycle analysis. Certainly for the UK projects that we know of, when they are looking for funding, they have to demonstrate the whole life cycle cost effectiveness. I don't know if there's one document that's done a whole assessment of them all. I think the problem is the scalability. No one's quite got a good handle on how much you would have to scale any one of these to know exactly what that life cycle analysis should be or would look like. So I mean, we're talking about for global mitigation of substance. I mean, something like the direct ocean carbon removal. I think it's something like 1% of the ocean would have to be um, pumped through these plants every year to get kind of the amount of carbon dioxide removal that we would need. That might be a slightly wrong number, but it's something in that order. So the scale is huge. And if we're doing that with just like small plants, like that's a huge amount of industry, right? And then where do you put it? Or do you put it on the coastal systems? Where do you put it on the coast? I mean, some people are talking about integrating them with something like wastewater management. So maybe you, or desalinization plants or existing industries already. And there's potential, like you could see maybe that those would help, but not, again, the scale is just insane, really, to think about the amount that would be needed. But yeah, absolutely, you need to be taking the whole life cycle. I mean, do we really want to be digging up our earth for more minerals just to counteract something which, like, yeah, yeah. So,
And water, right?
yeah.
The energy, like at least for my state, the one from the big water from it, and the cement comments.
Yeah.
Because they still can't read state companies and the energy companies.
So yeah, that's exactly it. It's the hard to decarbonize industries are the ones that are pushing it the most, as well as like the fossil fuel lobbyists. So it's those, and that's where CDR probably has the most potential. But do we just stick to conventional stuff? In which case, we need to move much more rapidly with emissions reductions, and we need to develop technologies that will help those hard to decarbonize groups. Or do we muck around kind of saying, let's do some of these and then get 10, 20 years down the line and we're kind of in a state where actually we really need to use these things, which we just don't understand properly. So, yeah. Two o'clock. Yeah.
And it's like that's what they're selling with what we know as well, because there's so much uncertainty in what we know.
Yeah. So I think that's on the hour. So,
So thank you so much. With that, I will journal. Most of the round table discussions. Let's see what it comes